All right, what I wanted to do here is just do a little bit of a review of where we even are in the class. So far, we've been doing circuits with a source, a path, and a load, right? We've been doing that the entire time. We've had DC sources for the first 6 weeks, then we moved to AC sources. AC means alternating current. So the voltage is changing back and forth, and the current is changing back and forth. It's alternating along this sinusoidal wave, which is why we put the AC inside of it. Now for the load, we've always needed a path to complete the load, otherwise it'd be a circuit. And if we had no load, but we just had a line here, right here, that would be called a short, right? Because there is no load, V equals IR, the voltage that is the potential difference across here. There is no R, there is no Z if we're doing V equals IZ inside of AC. And so because there is no, it's a short, current spikes, you have a fire, or you get severely injured if you make your body the short. So we've been putting loads in here, and inside of AC current, everything that we've had has been Z. Z being impedance, similar to the resistance in a DC current, the Z is impedance. Z can be a combo of R, L, or C. R being resistors, L being inductors that take time to build the current up. So remember, voltage leads current, Eli. For inductors and for capacitors, they look like this, where there's two plates. In these capacitors, it takes time for the voltage to build up. It doesn't change instantaneously. And so the current lags I, or you could say the current leads E, and we get ice. So that's why in these sinusoidal waves, we would say that the current leads the voltage, or the voltage leads the current, E being for voltage, right? So that is what is inside of Z. And now, we've been talking about the power. And so whenever we talk about power, we can always talk about the power from the source or the power delivered through the load, right? And we said that the main thing that we need to remember inside of alternating circuits, AC is a power triangle. And there's 4 components to this triangle right here. This should be a right angle. The 4 components are S, and I'll put it as the magnitude because remember this is a vector. So the magnitude of a vector is with this absolute value. The vertical component is Q, and the horizontal component is P. And what this is this lines up with our imaginary and real components, right? J, real, and so before we had an S vector, so now we just take this horizontal in vertical components and we turn it into a triangle. That's all that the power triangle is the real and imaginary components put into the form of a triangle. And the last piece is theta. And we said that S as a vector is called complex power. Complex, and it is made up of 2 parts in 2 different ways. We can say that it is apparent power with this theta. We could call it theta T for theta triangle. It's also the same as theta Z. Theta T equals theta Z. And that's because what it is equal to is the angle of V minus the angle of I. And so V over I would be Z equals V over I if V equals IZ. So if Z equals V over I, then whenever I divide the vectors, I subtract the angles, and that gives me theta Z. That is the same theta T that is inside of here. So this right here is apparent power. That right there is the theta angle inside of the triangle. So the triangle theta. But the other way, and this is the best part of this entire class, I think, is how easy it is to go from polar to rectangular, and it means something. Because if I go from polar to rectangular, in the polar form, I have apparent power. Well, in the rectangular form, I have my real and reactive powers, right? So this is real power, and this is reactive power. And that is enough, I think, to start with just understanding the power triangle. And then let's talk about how we would actually solve for some of these components in another video.